Welcome to 202E on parallel RLC circuits. How we view parallel circuits is significantly different than how we treat series circuits. So we're going to look at a few different ways to treat a parallel circuit. This lecture has been split into 3 different parts, one for each objective inside your module. But first, we're going to look at analyzing the behavior of a parallel RLC circuit. Now that we're dealing with parallel circuits, we have to remember that voltage is the same for all the different components inside our parallel circuit. Therefore, our voltage is going to be the reference. What this changes is how we look at the entire circuit on our phasor diagram. We still have Eli and I supplying, so we still have lagging voltage for IXL and we still have leading for IXC. However, when we put that on the chart, since my voltage is now my reference line, my current for my resistance is still in phase, but my current for my XL portion is now going to be at 270 degrees, and current for my XC portion is going to be at 90 degrees. IXC is still leading E, IXL is still lagging E, but the only thing that is different is how our perspective is when we look at our charts. The way we solve parallel circuits is significantly different than how we solve series circuits. In series, we relied directly on the impedance values. We determined what Z is going to be, and then we went from there. However, now it is in our best interest to be able to solve for each branch individually and then get our power and work with power triangles rather than working with impedance triangles. So put impedance triangles out of your mind. They don't work for parallel circuits anymore, but power triangles will. Let's analyze this circuit that is found inside your module. Here we have a parallel circuit with a resistor, a pure inductor, and a capacitor in it. The very first thing we want to do is find out what the total ampacity of the entire circuit is going to be. Keeping in mind that since we have 3 different types of devices, not only do we need to figure out what the ampacity per branch is, we also need to figure out what the phase angle of each branch is as well. We can use Ohm's law on each branch in order to figure out what exactly the current of each branch is, but we still have to keep in mind the phase angle, and then we need to put that onto our graph as well. Since the voltage is consistent, it's 120 volts across each different branch, and if we were to take Ohm's law and calculate it, we can see from our phasor diagram where everything lies. IR is going to be equal to 4 amps, IXC at 90 degrees is going to be equal to 3 amps, and IXL at 270 degrees is going to be equal to 2 amps. Once we have our individual branch currents and their respective angles, we can now put it either into an HV chart, or we can figure this out using Pythagorean's theorem. Keep in mind that if we're going to use Pythagoras, then XL and XC are going to cancel each other out. So therefore, my vertical component will be at 1 amp at 90 degrees. My resistive component is still 4 amps at 0 degrees. So using Pythagorean theorem, my I total ends up being 4.12 amps, and I can use trigonometry to calculate my angle at 14 degrees. That's method 1. Method 2 is to use the HV chart, in which case we want to put each ampacity at their angle onto our chart and figure out the horizontal and vertical component. This is essentially the same methodology where we will still have a total horizontal component of 4. I have a total vertical component of +1, therefore we can still use our trigonometry and our Pythagoras theorem in order to figure this out. Now that we figured out our phasor diagram for our currents and we have our total current and our phase angle for that current, we can take this information and build our power triangle. We use our power formula S is equal to E times I total in order to figure out what the total power of my system is going to be. Keep in mind that I can also use the same formula. P is equal to E times IR, and Q is equal to E times IX in order to figure out the other 2 sides of my triangle. The phase angle is the exact same angle that we saw in the phasor diagram for the currents. We have now finished evaluating what this parallel RLC circuit is going to do, and we can compare our results with what our actual measured values of the circuit is. We should be able to measure how much actual current is here, as well as the current through each one of our 3 branches. And we should also be able to compare our measured values with our calculated values for our power as well, both for our VA, our watts, and our VARs. We should also be able to determine what our phase angle is, as well as what our power factor is, in case we need to do any power factor correction. And we can also see whether or not this is a leading or lagging circuit. Since my ampacity for my capacitor is higher than the ampacity for my inductor, this is a leading circuit for us. This is the end of Objective 1. What I wanted you to get out of this objective is to understand how to simply break down a parallel RLC circuit. You need to find out what the ampacity of each individual branches are at their phase angle in order to find out what your total ampacity and the total phase angle for the entire circuit is. After you have your total ampacity as well as your phase angle, you can take that information to figure out all your power triangle aspects. You can rewatch this video as many times as you like, and then please go to Blackboard, then go ahead and do the knowledge check and move on to part 2.